Today we're taking a look at the graph of the function y equals ax squared plus bx plus c. Now remember, the graph of this function is a parabola. It's a quadratic equation. It has a degree 2, and it has the standard form of ax squared plus bx plus c. Now there's another form of this equation called the vertex form, and we actually touched upon it in our last lesson. Now the equation for vertex form goes like this: y is set equal to a times the quantity x minus h squared plus k. And we call this vertex form because when it's written in this form, the vertex of the parabola is found at h comma k. Now remember, the graph of all these parabolas has a domain of all reals. The range is going to differ if it opens up or if it opens down and where the vertex of that parabola lies. Now there's a special case of the graph of this function, and that special case represents the height of an object in free fall. This was discovered by Isaac Newton, really smart dude, really good looking, had some really long flowing hair, very distinguished fellow. Kind of looks like me actually if you look at his nose. I think he's got the same size nose as I do. What do you think? It's about the same size. I just need some cool hair like that. Anyways, Isaac Newton discovered this little formula here based off of gravity. It says -1/2 g, gravity, times t squared, your time in seconds, plus v sub 0, that's your initial velocity, upward velocity I should say, plus h sub 0, which is the initial height. Okay, so all of this strung together gives you the height of an object in t seconds. Now g, make sure you understand this, is the gravitational constant, and it is either 32 if we're measuring in feet, or it is 9.8. So we're going to take a look at a few of those specific examples here. Alright, in example 1 here, we're asked to show, are these two equations equivalent? And all we're doing here is we're comparing standard form to vertex form. So here's our standard form, here's our vertex form. In order for us to be able to determine if these two are equivalent, we have to solve out our vertex form and put it into standard form. So in order to do that, we're going to expand our binomial x plus 1 squared in the middle there, and then we'll distribute our 3 and subtract our 4. So here's what this is going to look like. X plus 1 quantity squared, remember that's the first term squared, plus 2 times the product of the two terms. Well, 1 times x is just x, so that's 2x, plus the last term squared. 1 squared is just 1. Alright, now following my order of operations, I need to distribute 3 to each one of those terms on the inside. That gives me 3x squared plus 6x plus 3, and then finally I'm going to subtract 4. Combining those like terms gives me 3x squared plus 6x minus 1. So you can see in standard form, in decreasing order of powers here, I have 3x squared plus 6x minus 1, and therefore they are equivalent equations. Okay, let's take a look at Isaac Newton's little formula here for an example 2. We have the height of a ball that's thrown off a cliff. It's thrown upward off a cliff. It's given by this equation. We have the height of the ball after t seconds will be equal to -16t squared plus 24t plus 75. Now keep in mind it was -1/2 g times t squared, that first term, plus our initial velocity times t plus our initial height. So this simply wants us to be able to recognize what is our initial upward velocity. That's the coefficient on t. That's 24. So that's given by 24, and this one's going to be in feet per second. And then how high was the cliff? Well, the cliff is the initial height at which the ball was thrown at, and that was 75 feet here. So you can see that I've graphed this equation out here just so you can see what it looks like. And there's some interesting points here. So the y-axis here has our y-intercept. That's going to contain our point at which the ball was thrown off the cliff. That's our initial height. And that's when time t equals 0. The next here is the vertex of that parabola. That's the maximum height the ball reaches. So when t is 0.75 seconds, the height of that ball is 84 feet. The next interesting point here to take a look at is where it crosses the x-axis again. In other words, my height is 0, so that's when it hits the ground. And our time here is 3.04 seconds, so about 3 seconds it takes for that ball to go up and then come crashing back down and hit the ground. All right, in our next example here, we're going to do a similar type exploration. We have a ball that's thrown from an initial height of 7 feet, and we want to find the height of that ball after t seconds. Okay, so we're asked to graph that function, and we're also asked to find some interesting points. So here's our function. This is what it looks like graphed on Desmos. I have my equation negative 16x squared plus 42x plus 7, where x is my time now. And you can see there's a couple of interesting points. Here's our y-intercept. That's the initial height which it takes off. The vertex of our parabola is the maximum height that ball reaches. And the x-intercept is the time it takes to hit that ground. All right, now if we want a table of values, remember we can go to Desmos, we can convert that to a table of values, and here are some good values that we can find. All right, now let's go back to our notes here and let's fill in some of those table of values. All right, at time t equals 0, we said our height was 7. At 1 second, our table showed 33 feet. At 2 seconds, we had 27. Negative 11, and negative 81. Now if we graph that, we're going to put time here on our x-axis, height here on our y-axis, and we'll just go up in increments of 5. Okay, now each little slash here on the x-axis will represent 1 second, and that should do it. So we'll change colors and we'll graph those points here. At 0 seconds, we took off from a height of 7. At 1 second, it looks like we were up to 33 feet, so about right here. And then at 2 seconds, we were back down to 27. And then at 3 seconds, we were actually below, so we'll go about right here. So our graph kind of takes on this shape about like this. And there's the height of our ball after t seconds. Okay, now part C to this says, explain what the pair of 4, negative 81 means. Well, 4 is going to be our time in seconds. So at 4 seconds, we're actually negative 81 feet, or we're 81 feet below the ground level. Okay, so it's actually hit the ground already. You can't actually travel negative 81 feet below ground level because that ball would bounce. All right, it says estimate when the ball hits the ground. So if you take a look at your table, we're somewhere between, 2 and 3 seconds. We were actually closer to that 3 seconds, and I think if we went back and checked our graph, it was right around 2.7 seconds. And then finally it says find the rate of change between t equals 0 and 1 and between t equals 1 and 2. So remember, your rate of change is your change in y over your change in x. So let's find the slope between 0 and 1 second. That is 33 minus 7 divided by 1 minus 0. And that gives us 26 over 1, which is 26 feet per second. Now our second slope here comes from when t is 1 and 2. So now we'll take our change in y, which is 27 minus 33, and divide that by 2 minus 1. So when we do that, we get negative 6 on the top, and we have a positive 1 on the bottom. So now our slope here, or our rate of change, is negative 6 feet per second, which should make sense because between 0 and 1 second, my ball is traveling upwards. So I should have a positive rate of change. And then between 1 and 2 seconds, my ball is traveling down, so I should have a negative rate of change. And therefore, we're going to say that our rate of changes are not equal to each other because gravity is having its effect and pulling that ball back down to Earth's surface.